Welcome back, Shaler area, to the Unit 2 Chemistry Note video number 12. So, we've learned about the atom, we've learned about the periodic table, and in the last note video we started talking about the electron cloud and its structure, and how it was the electrons in the outermost shell, or what we call the valence electrons, that actually interact between atoms and end up forming bonds. Today's note video is going to be about the kinds of bonds that they form. So atoms are most stable. They're at their most at ease. They don't react once they have full outer shells. This is the key. The key is that atoms want to have full outer shells to be at its most relaxed point. And that means they need 8 valence electrons, because that's how many there are in every shell, unless, of course, you're helium, and then you only want 2. So what can happen when these atoms start coming together if they don't have full outer shells? Well, they have to either give up electrons or somehow share electrons. And in these outer regions, depending on how far away they are on the periodic table, they do different things. So if they are really far away on the periodic table, like more than 3 columns away, they form what's called an ionic bond. And you may recognize this word here, ion, because remember, an ion is an atom that has a charge. So this is a bond that forms between 2 atoms, and the bond is the result of charges. So these form when one atom actually takes electrons from another. So it actually pulls the electrons from one atom, and now they're no longer that atom anymore. It has created an ion by stealing one of the electrons. Now, if you think about it, if you steal one of the electrons, what charge did you make that atom? Well, if you've stripped away one negative and it's no longer there anymore, you're going to have created a positive ion, a positive 1 ion. And then if you are the atom that's taking the electrons, you're going to be gaining a new electron. You're going to have an extra negative. So you're going to have an overall negative charge. You have this positive and negative charge between the 2 atoms. And this ends up creating a bond that's wholly due to electromagnetic force. These are like super tiny, kind of like little magnets sticking to each other in a way that is super duper strong. And as I said, if you are bonding together elements that are at least 3 families away on the periodic table, then this is the kind of bond that you are forming. So this is a very typical bond between things from all the way on the left of the periodic table with things all the way on the right, like a sodium chloride kind of bond. So what are some properties of things that form through ionic bonds? Well, ionic bond materials tend to form crystals. So if you ever see things that are made of crystals, those are molecules that are made from ionic bonds. They tend to have very regular shapes, super high melting points. So these magnetic forces, these electromagnetic forces that are holding the molecules and the atoms all in place, make it really hard for them to start vibrating out of control. They're really kind of locked in there. An example, salt. Salt doesn't start to melt until 800 degrees Celsius. That is ridiculously hot. It is super duper hot. Sugar also has a really high melting point. That's why that when you're making candy and you're melting sugar and you're making like hardtack out of it, it's really dangerous, because if you get that sugar on you, it is super hot when it's a liquid. So all ionic compounds can generally dissolve in water because they can separate into their positive and negative and kind of hang out and glide around inside the liquid. And this is what allows water to conduct electricity, because remember, neutral, like just regular pure water, will not conduct electricity. It has to have something like an ion dissolved into it. And this is what it would look like. Here's our sodium, here's our chlorine. Our chlorine needs 1 electron to have a full outer shell. Our sodium only has 1 electron in its outer shell. So if it got rid of it, its outer shell would now be the next one inside. It'd be this one. It would be the 2 orbital. Now that one has 8, and it's happy because its outer shell is full. if there's nothing in that outer shell, then it's like it doesn't exist. So by giving one away, it has a full outer shell. And by picking one up, chlorine has a full outer shell. That gives this a positive charge because it lost an electron. This one picked the electron up, so now it has a negative charge. And that electromagnetic force between the two creates the molecule. That's the bond. Well, if it's not an ionic bond, it could be a covalent bond. A covalent bond forms when atoms share electrons. They kind of cooperate in having a bond. Now, these kinds of bonds tend to form between atoms that are closer on the periodic table. Carbon, which is right in the middle if you think about it on the periodic table. If there's 8 columns, it's in column number 4. It always forms covalent bonds. Carbon doesn't form ionic bonds at all. And some things that are indicative of molecules made of covalent bonds, well, they're non-conductive, example, pure water again, and materials made from covalent bonds tend to have lower melting points, things like rubber, stuff like that. And a covalent bond forms, here we have an oxygen with an oxygen. This is a covalent bond, so 2 in the inner shell, so it's full, and then we need 8 in the outer ring. Well, we're going to share these 2. So if we count them, it's 1, 2, 3, 4, 5, 6, 7, 8. It has 8 in the oxygen. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 as well. So these 2 electrons are kind of zooming around. You could think of them sort of as doing like a figure 8 maybe. And the green ones are doing the same thing. So since they're going at pretty much the speed of light, they are actually everywhere along this line at once. And so it's full. They're going so fast that they are literally going around each of the atoms. Almost like in the TV show or the movie The Flash, where the Flash can run so fast he can go around in a circle and kind of be everywhere at once and make a wall. So they're sharing the electrons. And the same thing happens over here with the CH4. This is methane gas. This is actually the gas that comes out of the burners in the classroom that we use with our Bunsen burners, and the same gas that powers your stoves. The red electrons are probably from carbon. So there's normally 4 of them, and it needs 4 more. So we have a hydrogen one. So these ones are they're just kind of all cruising around, going around everything at once, and holding it all together. It's almost, instead of a electromagnetic force that's holding the molecule together, it's more of like a kinetic energy that's holding the molecule together. Now, since you saw in that other picture that you can be sharing more than one electron, there are single bonds, and single covalent bonds form whenever you're sharing 1 electron. You have double covalent bonds, that's when you're sharing 2 electrons. This is pretty common with oxygen, as you saw with many of the models that we made in class. Sometimes when we bond with an oxygen, we need that double bond. That's showing that it's sharing 2 electrons. And there is also a triple bond. And triple bonds form when you're sharing 3 electrons, and the most common thing this happens with is nitrogen. There's only a couple of other elements in the periodic table that will actually form a triple bond, but they're stronger. So the single bond is the weakest covalent, double bond is the middle, and then triple bond is the strongest. It's one of the reasons actually that nitrogen gas, this N2, which makes up most of our atmosphere, doesn't really react with anything, because this is a really strong bond. It's got full outer shells. It's super happy. We got, all 6 of these are zooming around, and the 2 are staying over here. It has no need to react with anything because it is like one of the most stable molecules in our environment. Now there is also something called a polar covalent bond, and this is a sort of a hybrid between the ionic and the covalent. It's a covalent bond because we have the sharing of electrons, but since we have atoms of different sizes, or if we have really big molecules that have like weird shaped ends, because it always comes down to the shape of the molecule, you can have these electrons, even though technically they're kind of like everywhere at once, they spend more time around a bigger atom than they would going around a smaller atom. So since the electrons need to spend more time going around the bigger section of the atom, or the bigger atom, that end of the molecule tends to be more negative, because the electrons spend more time on that side. And since the electrons spend more time on this side, it's more negative. That means the other side of the molecule ends up being a little bit more positive. Now, it's not a whole charge of a plus and a minus, but it's a partial charge, and it's the amount of partialness of the charge that actually has everything to do with the properties of these. But it's a pretty interesting bond. It allows for us to have chemicals that do lots of really unique and useful things. So it's a little bit more like a magnet. Water is the most common example and probably the smallest of the examples. This is what makes water a lot of the things that water does. And one of the most important things that works because of the polar covalent bonds are detergents or soaps. So they aren't polar covalent because of a larger atom, but instead it's a really big molecule. So on a detergent, we have this kind of like charged or water-loving end, and then we have a really long chain of carbons and hydrogens. And whenever you get a really long carbon-hydrogen chain, they hate water. They're called hydrophobic. This is the hydrophobic end, it hates water. This is the hydrophilic end, it likes water. This end can kind of pick up a charge. This end doesn't pick up a charge. And what happens is water is ionic, water is polar covalent. So it kind of has this partial charge thing going on. So it kind of sticks to the end with this little partial charge on this end. While oils and things like of that nature are not charged. They actually don't like charges at all. This is why oil and water doesn't mix. Well, the way that soaps work is you get oil on your skin. So here is your skin, this section right here. And then when you sweat or just, going through the day, your body creates an oil and it kind of coats the outside of your skin with it. This is a protective layer that your body manufactures. And it picks up all the dirt and the dust and grime from our environment. It kind of gets trapped in this oil. Well, in the old days, before soaps, people used to take steam baths and scrape that off with blades, like back in Roman times. But with soaps, what happens is the long ends, this long end of the molecule that doesn't have a charge, ends up kind of surrounding and attaching itself to the oils that don't have a charge. And if you're doing this while you're washing your hands, this blue stuff would be water. And the red ends love the water because they kind of have a charge, and so they're sort of partially attracted to the water molecules that kind of have a charge, and they end up forming these bubbles that go around the oil and make it possible for the water to wash the bubbles away and lift it off of your skin. So the reason that soaps work is because of the polar covalent bond, because one end of the molecule behaves differently from the other end. And the last and fourth bond is a metallic bond. And as you can guess, these are the kind of bonds that form in metals. In pure forms, in like pure elements, if you had 100% of the element, metals are pretty interesting, but not always that useful. Pure gold is really soft. It's so soft it would make really bad jewelry. If you had a gold ring and you put it on your finger, it would not stay round. It would kind of flatten out and pinch on you. It just would not hold its shape. So any kind of like artworkness that there would be to the jewelry that you would be making would be wasted. Pure iron is really strong, but the problem is it reacts quickly with oxygen in the air and it rusts, and then it turns completely useless. So you can make things out of iron if it was pure iron, and it would be fantastic for a year or two, and then it would fall apart. Well, that's not really going to help anybody with anything if you're trying to build it for long term. But an interesting thing you can do with metals is you can make what's called an alloy. And an alloy is a compound of metallic elements. And when you put them together, you get unique and interesting traits that kind of help counter each other out. So gold, jewelry, is never pure gold. It's always made of some kind of an alloy that either has some copper, some silver, some aluminum, or something like that in it. And it's actually the color that indicates what else is in there. So like white gold is a combination of gold and silver. And if you have like the copper in it, you can get some of this kind of a color. I think the aluminum might give it like an even like yellower color, although I'm not sure about that one. This is a ring that is done in the style. If you ever travel to where Devil's Tower is, or if you travel out to Mount Rushmore, it's the same area. The Badlands are out there, and it's a really beautiful part of the country, and the geology is pretty awesome. But they specialize in this kind of gold jewelry. It's really pretty. That uses all the different kinds of gold alloys. So when metals react with each other, they tend to lose electrons in the bond, and this gives the overall atom a positive charge. And we're not going to spend a whole lot of time talking about metallic bonds. It's important that you know what they are, and they actually, the fact that the metallic bond mechanism is so different from the other two is what gives metals all of their really interesting and useful properties. But the actual physics behind what's happening in the atom gets kind of complicated. You're not even going to learn a whole lot about this in high school chemistry. You won't really talk about the actual nature and mechanisms of what's going on in a metallic bond probably until you get to college, if you take chemistry in college. It gets pretty wild in there. So I'm going to try to break it down for you as general as I can. So you end up with these atoms that are kind of positive, and they're all kind of free floating in this shared sea of electrons. The electrons in a metal compound and like an alloy are shared amongst every single atom that there is. They're going everywhere, all over the place. And the more valence electrons that there are, the stronger the metallic bond is. This makes sense because if the electrons are all being shared equally amongst all of the atoms, the more electrons that are there are going to cause more electrons to be shared, and that's going to make a stronger bond. But since these electrons are like free flowing and constantly going everywhere, almost like a liquid would be, it gives the metals the ability to like flatten out and be ductile. If you hit the material, the atoms aren't kind of locked in place. If you actually are able to push those nuclei as a whole, think about like standing on one side of a line of desks in class and pushing really hard and moving the whole line of desks over. If we put all the desks together and you did that, you would kind of like make a dent in the material of desk. You'd have to push all of the desks in a line in order to get it to move. But that's what happens when you're pounding on metal. But you're hitting it so hard that the nuclei are all kind of moving or spreading out. It almost functions as a liquid. And since these electrons are also completely free-flowing, information, or if you would do something to impact the electrons on one end of the metal, it like almost instantly links to the other end of the metal. And this is where the conductivity works into play. The electrical conductivity, you're going to learn that electricity is nothing more than just the flow of electrons. So since electrons are all shared, they can pass from one side of the metal to another. And that's how we can use wires to conduct electricity. They're also a very heat conductor for the same kind of reason, even though that's more of a kinetic situation instead of electrical. The luster is a really interesting aspect of a metal, and it has to do with these electrons going all over the place. You don't really understand how luster and light generation works from atoms, but it has to do with like the way that electrons get excited if you can give them energy, and they jump into the next outer shell where they're not supposed to be because they have this extra energy. It's like they're all hopped up on sugar and they're running around the classroom. They shouldn't be, and then once they get tired again, they kind of go back and sit down in their seat, and when they give that energy off and drop back to their original orbit, the energy that they give off happens to be in the form of light. It's called a photon. And metal, since they have all these electrons going everywhere, the electrons can get excited really easily, and it just kind of is enough to make it like shimmer a little bit. Makes it very, very reflective. This is just a graphic to illustrate those three kinds of things. This one is kind of illustrating the lustery aspect of it, the fact it's going everywhere. This one's illustrating the electrical conductivity of it. If you affect the electrons on one side, you're going to almost instantly affect the ones on the other side. This is that like malleability feature where if you push in the middle, you kind of shove them all out of the way. As long as you can move them all, then it'll move. And that leads us to the end of this note video number 12. You got 13 questions coming up. Be sure to read in the description to get the link to the exit ticket questions for the video. Thanks. Have a nice day.